Yeah, so I guess welcome everybody again. It's good to see a lot of familiar faces and names in the chat. Today, I think it's gonna be good. I'm very excited for today's talk. Thank you all for. I think we moved, so thank you all for sticking with us in the date change. Um, yeah, I think that'll be it. I don't know if is there do we have stuff for next? Okay, we have that on the 5th, which I think is on our regular schedule. Okay. So anyway, I would say me again. So I'm Brandon Scott. So I'm still at South Dakota Mines, and I'm happy to be part of this with Claire. Again, Claire, if you want to take over again, that'd be great.
Sure. So I'm Claire Brown. I'm at McGill University in the Advanced Bioimaging Facility. And we were just asking if everybody could just put in the chat your name and your institution and or imaging facility. So we'll know who's here today. And if you want to, you can add what light sheet you work with and what field of research you work in, but we can leave those optional, as I know a lot of you have been to these meetings already before. So maybe if you're new, you could add those details. So we'll give people a minute to do that. So maybe while people are entering that in, I can just mention we have lots of activities coming up with BINA. So the scientific speaker series is continuing, and I believe we're overlapping with them today on June 13th at noon Eastern. There's also the BINA Career Series, which is the 3rd Wednesday of the month, and it's been really nice. They've been focusing on people who are working in companies and understanding their career paths. It's been really interesting to hear what people are doing. And then a save the date for September. We're really excited to have Bioimaging of the Americas, where we're going to have a combined week with Latin America Bioimaging and Bioimaging North America from September 25th to 29th in Morales State, just south, about 2 hours south of Mexico City. And the meeting is on a hacienda, and we'll have the whole hacienda, I guess, a resort to ourselves. So there's lots of outdoor space to gather in, and we're hoping to have some company representatives as well as lots of imaging scientists from around North America, South America, and Central America. So save the date for now. The registration will probably be open pretty soon. And then if any of you are interested, we also have the expansion microscopy user group, which normally meets on the 1st Wednesday of every month, but we also moved that meeting this month because of the ELMI meeting. So they're meeting tomorrow. If anybody wants more information, let me know. So I believe this was something that had come through our channels. So there's a Lattice Lightsheet 7 user meeting on July 11th, 2023, and this is in Lausanne. So this is in person. And to gain feedback about the strengths and weaknesses of the technology to share with SAIS. They're looking for anyone who's an active user, but if you're just interested in the technology, you're welcome to come as well. And it's in person at the EPFL in the BIOP microscopy facility in Lausanne. So there's going to be short talks regarding experiences with the instrument, starting in the morning around 10, and it will finish in the early evening. So the link is there if you're interested in registering for that. And then I'll turn it over to Brandon if you want to maybe do a quick introduction or have Christian introduce himself.
Sorry, I'm woefully unprepared to do an introduction. So I apologize, Christian, if you would.
No worries.
For me, the worst host.
No, that's cool. Thank you all for having me here. I think we kind of met on one Jan Zuckerberg online meeting, and I think there the idea came up that maybe I can give a talk here. So it's the first time I'm here, so I'm not really sure what you guys expect. So I will just do my best and hope that you find it interesting.
So maybe I
So,
could just say a bit more, Christian. We had been
yeah.
talking about with Lattice Lightsheet that one of the biggest challenges is the data. And last time we met, Brandon gave a presentation on how he's been using the Chimera software to look at his data. And so we decided it would be interesting to do a bit of a survey of the different software options that are out there. And then, you know, with your paper, it's perfectly aligned with these big data sets. So just to give you the backdrop.
Yeah, cool. Thank you. Thank you. That makes total sense. Okay, so I will share my screen. So, okay, you can see it, yeah? Okay, yeah. So I will talk a little bit about big image data processing. So, and to maybe introduce myself a little bit. So yeah, my name is Christian, and my recent activities you can see here. So from 2010 to 2017, I worked at the Advanced Light Microscopy facility at EMBL Heidelberg, and I was helping people with both microscopy and bioimage analysis. And actually, we also had a light sheet microscope there, or we still have it. That's why how this work that I will tell you about today came about. And so till 2017, I'm only doing bioimage analysis. So at EMBL, we have now also something called the Center for Bioimage Analysis, which should support people with all kind of image analysis. So that's my recent CV. So the talk is, so it's not Lattice Lightsheet, okay? So I already apologize. It's actually a movie light sheet from Luxendo, so normal light sheet, maybe you can call it. So there are two publications if you're curious. So the biological application was from a group at EMBL, Ashna Aladdin. The title is Tracking Cells in Epithelial Acini by Light Sheet Microscopy Reveals Proximity Effects in Breast Cancer Initiation. So you can look at this. It's an eLife publication. And then there is this tool that I developed initially for this project, but had also been used now by other people for other stuff, which is basically a Fiji plugin to sort of deal with this data. So the project biologically was this kind of data. It was actually really beautiful 3D data of these little organoids. And you can see here the green cells are actually tumor cells. And essentially what they then wanted to do is check under which conditions do these tumor cells proliferate more or less, yeah, because less is obviously good, then you don't get cancer. So that's just a very rough idea about the biology. And there were several parts. So they were acquired, the images, and then in terms of image analysis, there was some pre-processing of the data. And this is actually the only thing I will talk about today, because this is what this plugin allows. And then after that, we also had to segment the cells and track them. This we just did with Imaris. Okay, so nothing homemade. And as you will see, this was also possible because during the pre-processing, actually, we could kind of dramatically reduce the size of the data so that then the actual image analysis task was not so big data anymore. So that's actually also one of my main take-home messages, but I'm not sure if that applies for how you acquire data on the Lattice Lightsheet. So, but we will see. But yeah, so the challenge was that he had many of these movies, and each of them was about a terabyte, so already annoying enough to deal with. More specifically, so these were 2-color volumetric time-lapse data. And already the file format was a challenge. So these were Luxendo. Maybe some of you have a Luxendo machine. So I don't know what they do today, but back then they stored all of these in their own custom HDF5 file format. So, and the file format is 1 file per channel and time point, which I actually personally find a very reasonable choice. So I think that's a good idea in general. It chunks up the data in a kind of natural way that then each of these files contains 1 volume. It's not too big. So I think that's actually not too bad, but still, it's not the file format that you can just open with bioformat. So that was already problematic. So then we needed to do a series of processing steps. So first of all, we had actually wanted to bin the data because it was acquired with a camera that had a pixel size that was actually sort of too small for the biological question. So the resolution was too high and then the data was unnecessarily big, but they could not change it on the microscope because the camera was just what it was. So, and then also, I mean, not to lose the specimen during the movie, you'd acquire a bigger field of view than you actually have to. So we also wanted to crop it. Then it was actually a system with 2 cameras, if I remember right, and the channels were not super good aligned. So we had to shift between the 2. So we had to move them. And then also actually the sample was moving a bit. This was annoying for the there's some sort of echo or something. Does someone have their microphone on? No, I don't know. Okay, it's fine. So yeah, basically there was this sequence of steps and all of them had some parameters, right? And then the question was also, how do we efficiently do this, right? If you have a 1 terabyte movie, you don't want to try all these parameters without knowing what you get, right? So this was kind of the conceptual challenge. And then it's tough, right? You can't just play around with this and check how would it look if I bin it differently if it's a terabyte. You can't even load it. So this was kind of the challenge. And we didn't back then have a good solution. Maybe today, you know, this has several years ago, maybe there's more software that I'm not aware of, but back then there was nothing that we were aware of. So we actually wrote our own stuff. And then in the end, this resulted in this publication of this Big Data Processor 2 software. And and there is a publication, so you can read it. And there's also a GitHub repo, and I will actually now jump to this repo. So actually, I can also, if you want, maybe it's cool to put the link in the chat. Okay, so in this README, there's like most of the information. So basically, it's a Fiji plugin. And sorry, I just have to. Sorry, there was a distraction. Okay, and it builds upon Big Data Viewer. Maybe some of you have heard about it, right? So that's a Fiji plugin that's actually made for looking at big data. That's the point. And it builds on this ImageLib2 library, and also my whole code builds on that. And the good thing about this ImageLib2 was really designed from the scratch to deal with big data. I think this was one of their main points. So that actually, I think, separates it a bit from, for example, NumPy Python-based stuff, which I think was originally not designed for big data. Now with Dask and so on, you can actually make it work for big data, but was not the core design idea. But with ImageLib2, it's really all about lazy processing of everything. So I will come back to that. Yes, so the main features is that it's very lazy. So what do I mean by lazy? So the idea is, and I will show that in a minute, is that all the processing steps that you might want to do, like loading the data, even aligning the channels, even cropping and binning, are not actually done on the data. They are just applied on the fly only to the one plane that you currently look at of your data set. And this was the whole trick about this, I would say, that basically you could interactively, really literally within 1 minute, like adjust all processing parameters of this 1 terabyte data set, even move around really and check that it works everywhere without really doing it, okay? And then only once you're sure, okay, this really looks good everywhere, then you can actually say, okay, now I really want to do it. And then this takes hours, okay, on a normal computer. So, but okay, it works. You can just wait, or actually we also have, but that wouldn't now work out of the box somewhere else. So you can also just record a script and then kind of batch up, like put that on a cluster or something, and then like, for example, process each time point individually. So this is what we did, but this is just to tell you nothing that you get immediately out of the box, because that depends on your cluster and so on. But if you really want to use this and so on, then just contact me. We can get in touch. Yeah. But I think my main point today is maybe also not so much that you really have to use exactly my plugin, but I think if you have really big data, it's good conceptually to look for something that has this lazy idea, right? That it basically just virtually does stuff without applying it to all these terabytes, because that's really annoying if you then change your mind that you should have done something else. So this is, yeah.
Christian, sorry. On these, the interactivity as you're getting, is it CPU based? I presume. When you have, your batch, is there any GPU computing going on?
No, so that's a good point, and that's actually something where I'm not so sure now anymore whether what I'm doing is still state of the art, because now I think, for example, my colleague, and you all know him, Robert Hase, I mean, now he did a lot of GPU-based image analysis workflows in Python, and I never tried, but he sort of claims a little bit that this is so fast that maybe then you don't have to do it lazy anymore. Okay, but I don't know. I haven't tried. Okay, but it might change the game a little bit. Yeah.
Okay. Yeah. No. I mean, the lazy aspect of it, especially when you have multiple time points, right? You don't want them all loaded in all at once. So it's like a great.
I mean that for sure, but. Exactly. So yeah, I don't know, but I think this GPU processing, I don't support it, but it might change the game a little bit towards that. So I don't know. It's a very good point. Yeah.
Excellent.
Yeah. Okay. So then I will actually just show you here. So there's actually a bunch of movies on this README. Also one where we really do a whole workflow. So I will just show 2 of them because I think they sort of make the point. So this is okay. So this is basically the raw data. Okay. So this is the nuclei. This is one plane in the set stack, and then so this is just opening the data in Big Data Viewer and basically zooming around. And here I think you already see that this is many more pixels than you need, right? This is basically all just camera noise information that doesn't help you anywhere for your biological question. So it was clear that binning is a good idea. So, and then you can actually now basically get a binned view on your data, okay? And that's this view, and you can basically just play around and see how would my data look like if I would bin it that much. And it also shows you what would be the size afterwards, okay? And that is really dramatic, of course, especially in, I mean, okay, here we only binned in 2D, but these are huge factors, right? I mean, a binning by 3 by 3 is already 9 times less. So this is really not to be underestimated, I think. So I usually, before I do any image analysis, I always check whether I can downsample the data, okay, just as a default. So I highly recommend. I mean, the best is already, of course, if you acquire it, okay, and then you can check, and this looks actually better than before, right, biology-wise, and you can then move around in Z, and actually this was moving to different time points, and so you can freely browse through this whole 700 gigabyte movie, and it just applies the binning on the fly for just where you currently look. Okay, so that was basically the whole philosophy of this project. And then the second movie I want to show is this the same for cropping the data. This is now, okay, this is actually already binned, so you can change several steps. So here you actually see on the lower right corner, this is already a virtually binned version, not really binned, okay? And now you crop your virtually binned thing, and then you can then, this is actually a big data viewer bounding box, so you can again check like whether this is fine. And then it again tells you how quick the data would be now. And you could, again, okay, I don't show it, but you can move around in time and check again whether that makes sense and so on.
Was that swapping dimensions there? Did I?
Yes, exactly. I can play it again. So Yeah, this was a bit fast. So in big data view, exactly. So now we're looking in the XY plane.
Yep.
And then if you press for Shift X or something, you look along the X axis. So this is adjusting the bound, and then it's now exactly. So now we cut it at different planes, and actually big data view, you can have arbitrary plane slicing, but you can also have orthogonal.
Okay.
plane.
Very cool. Yeah, that's super
Yeah,
cool.
yeah, that's practical. And I'm a bit surprised now that it loads. I mean, depending on your file format, right? If it's a planar layout on disk, then usually this should take some time actually now, because so often then you have because you, like if it's a TIFF, for example, right? It's very fast to load one plane, but actually loading like this is not fast because this is not how it's stored.
Mhm.
And I think also so I don't, probably when I recorded the movie, maybe I already moved around a little bit. So normally you would expect that it takes a while till the whole thing fills up.
Wasn't that HDF5?
Yeah.
Wasn't
Huh?
that this was HDF5, wasn't it? Or did
Yeah, but it's not. But HDF5 per se doesn't mean. So they actually, I'm pretty sure, because they from Luxendo, I think their main criterion is to get the images away from the camera as fast as possible onto disk. So they don't do any clever 3D chunking. I think they basically store it like a TIFF.
Got it.
So internally, I think this should not behave much different from a TIFF stack.
Okay.
So I'm just now, again, this is some years ago, I'm now a bit surprised that it loaded so fast. So I don't remember why it's, but the good thing with Big Data Viewer is actually, compared to other viewers, it will not, like it can accept data that's not fully loaded and still stays interactive. So this is one of the cool features of it. Will not block you. You can move around while it's loading the data. So that's also pretty cool.
That's very cool.
Yeah. Okay. So yeah, so that's actually that. So if I go back to this presentation. So, and really here, and the other thing was, I don't show that now, the data came as 16-bit from the camera, but actually we just wanted to track cells and just want to measure, are they green or not? So we didn't care about this. So this allowed us, and this was also another factor of 2. And then this is really, I think this is really something one has to see once, right? This is a factor of 100, which I still find remarkable. And you don't do much, right? I mean, it's not horrible. You just 3x3 binning in XY. I mean, that just gets you a bit more isotropic resolution, cropping. So you do nothing crazy, right? And it's a factor of 100. So I think this is just really good to keep in mind that data can get really much smaller.
Exactly.
And then, yeah.
We do have a couple, I don't know, Claire, there's a couple questions that popped up in chat. Do we want to answer those in real time, or one was a very simple one. It was just, what other file formats can you recognize?
Yeah, that's a good point. So initially, when we developed this, we were really focusing on the Luxendo file format. So we wrote code to read this Luxendo HDF file format. But now, actually, thanks to a contribution from Nicolas Chiarotini, so he works at the microscopy facility at the EPFL Lausanne. So he wrote a Java library called Big Data Viewer Bioformats. So thanks to this, in principle, we can open everything that bioformats can open. So one has to see, I mean, if it's really big data, then details matter, how performant all of this is. But so essentially, everything that bioformat supports should work, and also with lazy loading. Okay, so this is the point what Nico did. So plus the Luxendo file formats, and plus actually doesn't really have, I would have to check maybe also some sort of file format, like when you, so there's also some regular expression options. So if you have a file format where you distribute your data across multiple files, right? Maybe each channel and time point void file, and then it's something reasonable like TIFF or so. We have also some regular expression options to load all of those. So that's basically the answer, yeah. And then, yes, okay. The other, Amira, okay. Approaches large data similarly. Okay, cool. Yeah, good to know. So if indeed, so I'm in this. Yeah, good to know. So I'm not claiming we are the only one doing that. Yeah, okay. So maybe Amira can do that too. Okay.
I wonder if you could comment, or maybe if others want to chime in as well, about the 16-bit versus 8-bit, because I was just having this conversation with a student yesterday with just some confocal data on expanded tissue. And I've always told people, like, keep as much information as possible. But then if you do want to quantify intensities, is 8-bit okay, or isn't it? And I mean, probably what we'll end up doing is some testing, but just curious what your advice would be there.
Yeah, so I mean, like I teach a lot of bioimage analysis, and I usually teach the people don't convert to other bit depths because it's tricky, right? I mean, so I mean, you definitely will lose something, right? Because you have less. So you have. So if you do this, you have to. I mean, first of all, have a good reason, and I think here we had a good reason because we don't. Yes, I mean, it was just big data, and then of course you should know what you're doing. So for example, if you then still want to, for example, compare different data sets, then you should, for example, convert from 16 to 8-bit, probably not with some min-max algorithm, but basically have a fixed recipe, right? Maybe, gray value of 1000 in 16-bit goes to 0, and a gray value of 30,572 goes to 255, and you do this always, right? And then you will not lose, right, stuff like that. But yeah,
I guess another option could be to use the 8-bit to do your segmentation and then go back to the 16-bit data for your analysis.
Fair enough. Yeah, that's also an idea. Yes, I like it. Yeah.
Thank you.
Yeah. Okay, so and as I mentioned, then to actually really do it on this rather big data set, the whole thing also comes with macro recording, and then actually you can record everything and then basically execute that on some other computer, right? Because this you can actually do on your laptop, but then maybe or you even then, and I could help. We have some logic that then you say, don't do this for all time points, but just for a few, because then you can parallelize. Because actually this is, in this case, you can trivially parallelize over the time points. So that's the idea. So yeah, this is just a summary. So I'm actually already getting to the end. I hope I'm not too short, but better too short than too long, I guess. So I mean, obviously, most of the things I'm showing, if you already do the right thing on the microscope, then you basically sort of don't need my tool, right? We had actually this practical problem that just the camera was not very flexible. So there was just a certain bit depth and a certain pixel size, which was both too much for the project. But if you can adjust that, then maybe, exactly. And then, I think most of the things I said. And then, I want to thank the people that were involved back then. So there were like the biological parts, and then we had Ashish who helped developing actually some of the Java code. And then Nicolas, yes, I want to mention because he contributed, as I said, some of these readers, which is of course key, right? You have to open your data in a good way. That's the whole point, actually. And then, thank you for the Chan Zuckerberg initiative for currently paying my salary, which is very nice. And so it's already it.
Excellent, thank you, Christian. That was super interesting. There's like the intermediate bit depths as well, right? So there's like 16-bit, but also like 12-bit, which like that's where I feel like a lot of the biological cameras really should be. 8-bit, obviously 256, 255, not quite enough, but 65,000 on a light sheet. Like I don't think I've never once ever come close to that.
No. And I think there the issue is then that this sort of standard libraries, I mean, for example, Fiji, I mean, it just has 8 and 16-bit, and I think also we just now finished a course using scikit image in Python, which is also like a standard, I would say, and they have also just 8, 16. So I mean, like in terms of then having efficient compute, 12-bit doesn't really help you because most libraries actually then anyway do it with 16, right? I guess. I don't know.
Right. Yeah.
Or memory. Yeah. Or maybe you can, I don't even know if maybe on disk. Yeah, but that's I think a bit like the issue with things like 12-bit. I think the sort of file format and software ecosystem doesn't really support,
Of course.
at least as far as I know.
Yeah. Right.
Yeah, I think Alex is making the same point in the chat there, that even if you have
exactly.
12-bit image, the computer was stored as a 16-bit.
Yeah, that's a bit of the thing with this. Yeah. Unfortunately, that doesn't then help so much in the end.
Yep.
Yeah.
Are you continuing to develop this application?
So I did over the last year. So there were a couple of other institutions where I regularly got issues on the GitHub and I fixed them. So I have to say, unfortunately, internally, I don't know, maybe you can give us some feedback how this is for you. So we had in the facility actually a bit of an issue to get many Lightsheet projects going. So I think it somehow was for most of the people, it turned out then they were somehow too much with all the sample prep and so on. So this was actually taking a little bit less off than we hoped initially in terms of Lightsheet at the advanced light microscopy facility. So there were not, so then I was mainly actually, it was more than people from other institutions that wanted to use my software. So I don't know. So curious to hear whether you guys have different experiences.
We had a Lightsheet that we were managing as well. And my sense was that we really needed a dedicated person to work with people for the sample prep and the image analysis. Well, even probably more than one dedicated person, right? It's not necessarily the same person helping with sample prep and image acquisition as image analysis. And we had a similar experience that we had somebody kind of doing it in their free time, and we had some staffing turnover, and then it takes a long time for the new people to get up to speed, and with only 1 or 2 users, is it worth it? And so a very similar experience, I think.
I see.
We're hoping with our Lattice Lightsheet that we'll have better luck, but I'm trying to get one of my staff to really be dedicated to the instrument at least 3 or 4 days a week. So to me, I think that's the key is if people are going to try something new and complex like this, they need the support, and then once they're up and running, they can certainly be independent, but it might take a month or 2, so.
Okay, interesting. Yes.
I don't know if anybody else wants to comment on that aspect. How does it go for people with the home built or the 3i system when you're teaching people how to mount their samples? Does that take a lot of time, or is it something that once you've kind of got it, you've got it?
I'll give others a chance, but I have experience in this, and I think it took us a long time initially, but now it's no time at all for new people, and so once we internally figured out what we were doing, now like I have an undergraduate who I trained to be independent on the microscope in a day, and that's just an undergraduate researcher, and so it's like that's the thing that always makes me kind of chuckle when everyone's like, oh, I can't ever do this. I'm like, no, you definitely, like, it's very doable to get people up and running fairly quickly. But having the processes in place, I think, is really what made that happen for us. It's, I guess, when that's the only instrument you have, you kind of have to get good at it or you fail, right? Whereas if you have others that are easier to use, and I think that's the thing, is there's a bit of activation energy that people have to put in to use it, and there are always easier ones to use, right? Easier.
Yeah, exactly.
I think that's the problem, right? If the activation energy is too high, they're like, the gain I'm getting is not worth it. I'm just going to go to the confocal where I know I can get reliable data every day. And, so that's where I think having the staff is such a key.
Right.
I think for us was also, I mean, we actually had the staff, but I think there was also this other aspect that the whole Luxendo company was also still pretty young. So also the product, I think, was still like, was not the size LSM 510 or something, right? And then also there were still hiccups and so on. And then of course you can't fix this on your own. And so I think it was also a mix of this, that the technology from the commercial side was not at that time completely, rock solid or something. Yeah.
Mhm.
Probably much better now.
Yeah, Alex, I see your points in here. I don't know if you want to hop on, and if you're willing to hop on and chat on that. Be interesting. It might be easier than the back and forth text, just to get your thoughts on that, on the bit depths.
Yes, what did you want to know exactly?
Well, so you were claiming here, right, the 8-bit versus 16-bit, or maybe 12 or 16 for machine learning. So it'd be a new thought for me. So why would 16-bit be required if all of your data, if you weren't doing any like saturation, right? So if your data, for example, fit within 8-bit, how would having just a 16-bit image be beneficial to you if your data only went from 0 to 255 naturally?
Right. Well, oftentimes in like convolutional neural networks, there will be an initial normalization step. And if you do that, then if your data spanned along the range of whatever the minimum and maximum bounds were, I think you're fine. But no, I don't know. I'm a bit speculating here in the chat. I'm really not sure. Obviously, there's more information possible. There's more steps you can occupy with a higher bit depth. I think we all know that though. But yeah, I mean, potentially, during that normalization step, if you have a different range of values, that could be a feature that your machine learning algorithm picks up on. I'm much less familiar with like denoising algorithms using AI. That's in particular where I think this would be relevant. So maybe that's why I hesitate to give a definitive answer.
Yeah, I think it'd be a great thing to test for sure. And really just show, the impact of it and how what kind of magnitude it might be,
Yeah.
I think it's something we don't think a lot about, right? So
I don't think it's too mysterious, especially if you have a normalization step, because I know in a lot of the tools I've used, the data will be normalized as a floating point from 0 to 1, and that helps the prediction be useful on other data sets regardless of their bit depth. So you could imagine someone trained like a segmentation on 8-bit data, then later they want to do a prediction of segmentation on 16-bit data. Well, would it work? If you had normalized the input to the model and then you do the same thing during the prediction, then yes, that should work fine. Otherwise, you'd have to downsample your data before using the prediction, I think. That's just what I know, but I'm by no means an expert. I use a few tools, but certainly not all of them.
Sure. Well, and they're going to floating point though. That is more like that's even more. Right? That's like 32-bit depth is typically what a floating point is going to be. And so
yeah, but well, it sounds like a lot, but deep learning, well, machine learning, it's generally taking chunks of your data and passing them through a model rather than taking the entire data set. Like you're not taking 700 gigabytes of data and passing it through a neural network all at once. I don't think even the incredible feats at Microsoft and Google are capable of such a thing. instead, tiny snippets of data are plucked, and those are going to be the portions that are converted. So it's not like you have to keep a 32-bit float copy of your full-sized input image on hand in memory to do that normalization step. I guess you could implement it that way. It's just pretty wasteful.
Mhm.
No, I don't want to mince words. Deep learning is generally pretty memory intensive, so do a little study of your own hardware to see if you can do what you're trying to do. But yeah, that shouldn't be a deal breaker.
So Christian, you might have answered this already, but I forget. So answer it again, please. So your new bioimaging analysis center, where you're currently located. What's the latest and greatest that you guys are pumping out now?
So we are actually, it's not my mission necessarily to develop stuff, but actually it's more like a facility. Yeah. So
Okay.
to like make stuff usable. So, but I mean, something we just played with, and I think it's also not super new conceptually, but I think I have just never tried. I mean, do you know, like deep learning wise, do you know YOLO?
I might have heard it.
So okay, so YOLO is, you can Google it later. That's one of the most used. So this is a tool for object detection. So this is basically like if you give it a picture, it can tell you, it makes bounding boxes, like here is a car, here is a pedestrian, here is a tree, and that stuff like that. And I always thought, because what we do actually quite a lot at EMBL, we do this sort of intelligent microscopy things, where I don't know whether you guys also doing that. Basically, the idea is you take a low res image and then you find your cells of interest and then you zoom in automatically and that, right? And I always thought for this, these models are perfect because you actually, exactly that, right? You have a low res overview image. Here's my mitotic cells. I just need the bounding box and bam. And so, I mean, this is just what we played with the last couple of weeks. And it looks really very nice. So you can actually train it very easily. Just so I think, yeah, that was just comes to my mind now because this was like, I thought this is cool. These object detection machine learning models, if you want to do this smart microscopy things. I don't know whether any of you here are into that, but so we do this actually quite a bit. And
Cool.
I thought this is a nice reusable tool. The other things, just to say something, sort of, I mean, first, okay, then in terms of image file formats, right, we are trying to adopt somehow OME-ZAR. Probably you've all heard about it. I mean, it's there now and it's functional, but still to use it daily life is a different story, right? You need all the tools to be able to read and write it. And this is actually something which is not the case. So I think we're just slowly trying to sort of get there, yeah. But also we can't do this alone, obviously. So, but it has to evolve. The other buzzword I can say, so I'm also like actually making image analysis workflows, right? So then typically you have multiple steps, and there the question is also, how do you chain them? So what do you use for chaining them? And especially if it might be tools that are different programming language, maybe you have a Java tool and a Python tool, and in the end you want to do some R or something. So there we are exploring this, it's called Nextflow. So this is some workflow management stuff that has been around for a long time, but not used much in imaging. So I think this is another sort of bigger thing where we're trying stuff out now in terms of maybe something that's not yet completely standard. So yeah. So
That's always our biggest issue is having to change between languages. So it's always going Python or MATLAB or BAC.
Yeah.
So this next flow is basically like an umbrella. So it'll just send out jobs to each of those and link them together.
Yeah, exactly. I mean, basically what you need to have for that, basically each step in the pipeline is essentially a command line executable that takes a file as an input and a file as an output. And then, so this is what you need. And then it can be any, it just has to, and it supports all the different ways of installing these tools like Conda, Docker, Singularity, all of that. So Nextflow has logic for all of that. So you can then build I mean, again, it's still annoying, right? You have to still do all of that. But yeah, but somehow, but what's really cool about this is that it's once you have it like that, for example, it's very easy then to just say, okay, don't run it on my local computer, but on a cluster or something. So it has all the logic for that inbuilt and so on. So I think it's cool. And we tried now already for quite some time, and so far I still think it's a could be a good option. Yeah. So
Yeah, that's cool.
So yeah, these are maybe some of the things we just recently tried. All right. Different topic from Lutz.
Yeah.
Actually, that's a good segue because that's what our topic is going to be for the next meeting. So not necessarily deconvolution per se, but I guess we could build that in. Just go back to our slides.
It's a large topic, right? So
yeah, so the plan right now is that we will have a presentation from Zeiss on how they're doing data visualization and analysis with the Lattice Lightsheet 7. So we could perhaps bring deconvolution into that conversation if there's time. I don't know if anyone has a comment right now. We do have a few minutes. So our next meeting is September 5th at 12 Eastern. So same time as today, 12 Eastern, 11 Central.
And it looks like maybe Lutz, it works for Zeiss. Is that correct? So that might be, yeah.
yes, for the last 30 years already. So there is pretty much my domain.
So is that built in the software?
Yeah.
Mm-hmm.
And so
advantageous because of the data sizes that are.
Mm-hmm.
So what are you doing differently than others might be doing? I'm assuming naively that it's going to be something like a Richardson Lucy. Are you doing something particular?
Well, we have a lot of algorithms actually. Would work as a conjugate gradient algorithm that it's critical for lattice light. It would be a talk all by itself. How points, but because you have these side lobes, right? That I'm using the GPU spec that we have lots and lots of data.
Sounds like we're cutting in.
Have a bad connection.
I think so.
Yeah, it says it's unstable. Here, it's kind of strange. It's the first time I'm using Zoom, by the way. I'm more used to the meeting where I never had a problem actually, but I have to look into the settings maybe later.
Yeah, so maybe we could have that as one of the topics for, maybe we can have that as one of the topics in September if there's time.
Right.
Okay. Okay.
It's just hard to hear. You're cutting out quite a bit.
Yeah, every third word, unfortunately. But yeah, I think that would be super interesting. You know, I certainly have thoughts on the side lobes being useful out of focus fluorescence. I I think that's a bit to me. I'll keep those thoughts to myself for right now, just because they're symmetric. So you can't tell if it's above or below. Like, stop it.
No,
So anyway,
so you cannot just scrap them out. So, well, it also depends. Yeah, the lattice light sheet is kind of fixed, right? There's not has for the different wavelengths. It has different scaling part of that of the process, right? So and they have to be considered, because if you right in the result, so work shares.
It's really cutting out, so we can only hear every second or third word. So,
Oh,
yeah, it's not at Nyquist.
Yeah, something like.
Yeah, it's that. I don't know. Is it Zoom that is so bad?
it's hard to say.
It's
I
hard to.
I don't think so, because we're not having trouble with anyone else. So
think it's just your connection.
Mhm.
This time, I guess, but I just wanted to show quickly
Yeah.
effects of the side lobe and the alignment. I don't know if you can.
Right. No, I totally understand the idea of the side lobes, but my I guess consternation is side lobes here are symmetric on either side, right? If it's well aligned. And the argument that a wide field out of focus fluorescence is useless and it's just adding blur, but blur from structured light that is symmetrically about the focal plane is somehow inherently useful. Is to me a bit of salesmanship. It's out of focus symmetrically on both sides. We have a very good model to fit what the wide field PSF is, and so if you can do that, but if you can't do that, but you can now do this other one, that to me just sounds like nonsense.
Well,
as we're talking about that, that's really the heart of my.
This is not a wide field point spot function, right? I mean, it's the product.
Of course, it's not a wide field. But what I'm saying,
functions, and don't forget you can have of the time. Well, most of the time you have in they are there, and you know if you don't correct them out of alignment. So I think you are talking that might be a. I mean, I'm doing this deconvolution for a long time, so at another time. Hello.
Yeah, sorry. Can't. Again, we're very much undersampled in our conversation here. Maybe we'll have to try and have this conversation offline. I think maybe next. I think this would be a great. So what I would say, I guess Team Zeiss is up in September. Anyway, that's correct, Claire? Correct.
Yeah.
So I think this would be a phenomenal addition to that conversation at that time. So I think Renee had reached out there. So I don't know what the plan is for all of that. Like, this is the type of science that we would love to see here, right? And describing how you guys are suggesting that these are working.
Well, just here in this non-fitting point spot function.
Makes sense to continue, Lutz, because we really can't hear what you're saying. So And hopefully we can get a good connection in September. We could maybe run a test ahead of time.
Right. I think that'd be really good. Because yeah, I mean, I think this gets at the heart of what we are hoping to discuss, and what sort of things that the companies on one hand are bringing to the table, and then what some of the others, more academics, are bringing to the table as well. So I think that would be a really good discussion. So hopefully we will have a much better connection. So like Claire was saying, we'll test it out and beforehand and to make sure that we're not fighting technology on that end. So I do think anyway, we are actually getting to time, so this is like a really great discussion all around, I think. So again, Christian, thank you so much for today. This is really cool stuff that you're doing.
Yeah, thanks for the invitation. Yeah, thank you. It was fun.
Thank you. And hope to everybody has some nice time for vacation over the summer, and we look forward to seeing everybody in September.
Excellent.
Okay. Bye-bye.
Ciao.